All right, welcome everybody. So we're very lucky to have Scott Swinton with us to speak. Scott is the ARE's Henry Schapper Fellow. It's something that we do in ARES each year in the WA branch. We try to bring in a prominent international or sometimes Eastern States Australian speaker to do several things while they're here. Scott's been very busy. He gave a lecture on Tuesday. He's done a couple of workshops with PhD students and early career professionals this week, and now he's giving this seminar today. Scott is a professor in the Department of Agricultural Economics at Michigan State University in the US. He's a former head of department of that department. He's a former president of the Agricultural and Applied Economics Association in the US, and also a fellow of that association. So he's got an amazing track record, an amazing set of publications. So I'm confident that you'll enjoy and learn from his presentation today, which focuses on risk in agriculture. Over to Scott.
Well, thank you, Dave. Is this working well? Can you hear me? So it's a pleasure and honor to be here. It's been a really fun week. You've got a very stimulating group, and this is an exciting place to be, and it's been exciting to me to be here with you. I want to talk with you about something that we all face in agriculture, and that is climate change and how farmers will adapt to it. And so the research I'm going to present is research with my PhD advisee, Natalie Loduca, with whom I spoke this morning at 7 a.m., which was 6 p.m. the previous day, her time. And so this research, the paper is entitled Measuring Farmer Risk Aversion and its Effect on Perceived Crop Yield Distributions. I'll make those connections for you as we go forward. So, how will farmers adapt to climate change? Well, partly that's a function of what climate change do they foresee. So if weather is changing, then the probability distribution of future weather is changing, and with that, the probability distribution of crop yields. So if farmers are trying to manage the risk of a probability distribution of crop yields, it becomes important to understand what is the probability distribution that they perceive, because it's what they perceive that's going to drive their actions as managers. So where do risk attitudes fit? Well, we know from prior research that risk attitudes affect managerial decisions directly, but we also know that they may affect the very way that people perceive probability distributions. In other words, there's some evidence that people who are more risk averse perceive a higher probability of bad things happening than people who are less risk averse. So let's think about changing weather. When I, at my graduate training, and we studied risk analysis, we assumed that there was some probability distribution of outcomes. And we didn't think about whether those distributions were static or dynamic. I simply took them as being static. And so the question was, did the manager understand the true underlying distribution or not? But now in a world where we see evolving dynamic probability distributions, we have to think about not only what's the probability distribution that managers experienced in the past, but what are they expecting in the future? So, and you know, here, I can't speak about the management of agricultural risk without indicating how much all of us around the world owe to Australian researchers. I mean, the single most important book for me in thinking about applied risk management was the Anderson, Dillon, and Hardacre textbook that came out of that incredibly creative body of work from University of New England in the 1970s, and of course John Quiggin's subsequent work. So if subjective probability distributions shape action choices, then I asserted a minute ago that there's a role for risk attitudes in shaping those subjective distributions. And that partly comes from some research in ag economics by Menepace et al. With some work in Italy. So with this in mind, in today's talk, we're going to start with risk attitudes and estimating risk aversion levels, and then use that information to look at subjective probability distributions. Here's the itinerary. So I'll walk you through how we elicited risk attitudes from farmers in the US, how we chose the best model for that. You may quibble with how we did it. We can talk about that. How we elicited the farmers' subjective perceptions of future yield distributions. The relationship then between risk aversion and those future distributions that they perceived. And finally, what motivated, the applied question that motivates all this is, how is this going to change? How is this going to affect the way that farmers adapt to climate change? So there is a literature out there on crop yield risk in the field, and experimental literature. And the oldest pieces, and pieces that have gotten recited extensively, is the incredibly creative work by Hans Binswanger around Hyderabad, India, which he published in 1980, which used experimental methods in the field to elicit how farmers perceived risk. So these were risky gambles that they were confronted with. There's been subsequent recent work by Cerrone et al. On Scottish potato farmers that has measured their risk aversion. But an awful lot of the work on risk aversion, on eliciting risk attitudes, has been work that is in the lab, or work that is simply assumed. I mean, I would say the vast majority of articles about how farmers manage risk aversion assumes a risk aversion level and then says, if people behave that way, then here are the inferences that we can make. On subjective probabilities in agriculture, I mentioned the Menepace et al. Piece, which they were looking at Italian apple growers and found that more risk-averse apple growers were likely to perceive larger crop losses from pest damage. So none of this bears on climate change risk directly, but it's all relevant to climate change risk. So our objectives: elicit from farmers their risk attitudes, elicit from them their subjective perceptions of yield distributions of an ag crop, and figure out what shapes those perceptions, and then look at the effects of their climate change adaptation tactics on possible adaptation tactics like use irrigation, use drainage, plant drought resistant seed. What effects will those have? What effects do farmers believe those will have on future probability distributions? So we're going to do this with field experiments and interviews. So first, let me just do a quick trot for anybody who needs a refresher or an introduction to ways to think about risk aversion. So the key insights from what's called expected utility theory posits that so here on the vertical axis we have utility. So that's the satisfaction, it's the objective of the decision maker. And on the horizontal axis we have some outcome variable. So you can think of this as the values of payoffs. X1 is one payoff. That's a low value payoff. X2 is a higher value payoff. And so what you can see here from the shape, from this curve, is that people get decreasing, we're assuming in this curve that people get decreasing marginal utility from higher payoffs. And here's what that means. E of X is the mean of X1 and X2. So if you have a gamble that's a 50% probability of X1, 50% probability of X2, the expected value is E of X. Now, this risk-averse decision maker, the dashed line between where X1 hits the utility curve and where X2 hits the utility curve, this dashed line connects those 2 points. And you see the dashed line is below the utility curve. And what that means is that this decision maker gets less satisfaction out of the expected value of this risky gamble than they would get if they could have that risky gamble for sure up on the top of the utility curve. What it also means is that we can think of a value that we call the certainty equivalent. That's XCE here. That is the amount that if this decision maker could have that for certain, they would be indifferent between having less money, XCE for sure, or a risky gamble between X1 and X2 that has an expected value of E of X. And for our purposes here, the key point is that the difference between that certainty equivalent and the expected value of the gamble is what we can think of as a risk premium. So this decision maker would be, because I said they're indifferent between XCE or E of X, another way to think about this is they would be willing to pay pi, this much in order to have XCE for sure, rather than to take this risky gamble. So this becomes then a measure of how risk averse the person is. So if the more sharply curved this utility function, the larger will be the risk premium. And so in this research, we're going to be interested in how risk averse an individual is, and that has to do with how curved this utility function is. Well, there are, thanks to some great thinkers like Kenneth Arrow and John Pratt, there are some functional forms that can describe utility functions that curve in fairly clear, simple ways. So one is a functional form for what's called absolute risk aversion, and that measures the degree of risk aversion as a function of risky gamble values in absolute monetary values. And it takes this exponential form where utility of some level of wealth is equal to e to the negative alpha w. What you should pay attention to here is alpha is the coefficient of absolute risk aversion. So that is the coefficient here that measures that degree of curvature that we're interested in. So this is when we're measuring in absolute quantities of money. So this would, based on absolute risk aversion, a risky gamble that has $5,000 of difference between the low outcome and the high outcome, the decision maker would be indifferent between doing that if they start with no money at all versus doing that if they start with $200,000. A different way of looking at this is through what's called relative risk aversion. And this looks at the proportional change in income, the proportional change in the outcome variable relative to what you had to begin with. And there's a functional form for this also. It's of the form that you see below. Here, the coefficient that we care about is R. So the beauty of both of these, and there's lots of literature on this, we're not going to go into that, but the beauty of both of these is that these functions reduce to a single variable that can tell you how risk averse that individual is. Now, a newer function that's been introduced is one that nests both of those. So it's called the expo power function, and it allows us to express both of those in a way that now can capture both absolute risk aversion, relative risk aversion, and some mix of the two. So this is a more flexible functional form. It imposes less restrictions because, remember, whenever we take a certain functional form, we are imposing that functional form on the rest of the analysis. So this gives us a little more flexibility. But those two that I showed you earlier are nested in this, in the sense that if the R, relative risk aversion coefficient, approaches 0, then this reduces to constant absolute risk aversion. If the alpha coefficient approaches 0, then this reduces to constant relative risk aversion. And as a heads up, I always prefer a more parsimonious model, so I'm going to hope that we can get to a simpler model here. But I want to start with something that's more flexible. The nice thing about the expo power function is that unlike a constant risk aversion function, it admits the possibility of risk aversion that may decrease as a person's wealth increases. And there's reason to think that that's a reasonable assumption, that for a very wealthy person, gambling with a little bit of money is just not, it's trivial, and they don't, they're fairly indifferent about risk there. And this also includes the possibility of increasing risk aversion. So it's quite flexible. Okay, we're applied economists here. We're going to bring this to data. And this is based on lottery interviews with 44 farmers in these. So we selected farmers who had at least 300 acres, so that's 120 hectares, and who grew either maize or soybeans, which are the predominant field crops in the central United States. These data are all from the southern part of the state of Michigan, where I work. And so we have, this is in the temperate zone, humid. This is rain-fed agriculture for predominantly. But what we're seeing with climate change in our corner of the world is not big changes in temperature, but a lengthening of the season without frost. So the non-agricultural season for us is when it's too cold to grow things. And when rain does come, it comes in larger amounts and less frequently. And my ecologist friends call that flashier rainfall. So this increases the risk of in-season drought or periods of excess moisture, so in-field flooding. So for each of the farmers answered a set of 25 general lottery questions that I'll describe, and 18 questions related to agricultural lotteries. And then on the yield, subjective yield distributions, we elicited from them what are called triangular distributions of crop yield, asking them to think about yields that they'd experienced over the previous 10 years. And then we gave them a ceteris paribus assumption, and we said, assume that you're using the same seed and the same technologies. What yields would you expect in the next 10 years? Yes. We told them that we would give them a payoff based on a randomly drawn answer, one of their randomly drawn answers on the general lottery. And the payoff was pretty modest, Steve, because we're asking them, as you can see here, about tens or hundreds of thousands of dollars. So we took those numbers and we divided them by 4,000. And so what we did in terms of incentives, we paid them $50 to come to the interview. These were in-person interviews with graduate students. And they were given $50 for showing up, and they were given $40 to play with. They got $50 directly for showing up, and they were told they weren't given the $40, but you have $40 and your payoff will be based on that $40. So they could lose or gain from that $40. So it's still a windfall to them, but there was a little skin in the game. So here's how the general lotteries worked. They went through this exercise 25 different times. And the lotteries included ones where they had choices that were both positive payoffs, both negative payoffs, and positive mixed with negative payoffs. So here's an example of one that's positive mixed with negative. Which lottery do you prefer? In lottery A, you have a 40% chance of gaining $100,000 versus a 60% chance of losing $80,000. Lottery B, you have a 25% chance of gaining $10,000 and a 75% chance of losing $40,000. And so the experiment was designed so that we would have strong statistical power at deriving, at estimating risk preferences. The agricultural lotteries, we linked to particular agricultural investments of three sorts. You can invest in increased drainage tile. We live in a part of the world that has a lot of heavy soils. So in fact, in many parts of Michigan, agriculture did not really become feasible until farmers developed ways of draining what was fairly boggy land. This may be a hard concept if you're here in Western Australia, but this is what our corner of the world is like. Irrigation is another investment they could consider. And finally, a low-cost investment was investment in drought-tolerant seeds. And we also had some scenarios about crop insurance, but I'm not going to talk about those right now. So here's how these went. So these had a little bit more detail to them. Suppose there's a 10% chance that your field floods during the crop season and a 90% chance that your field will not flood. You can invest in tile drainage at a 60-foot spacing. This will cost $726 per acre, which is an annualized cost of $1,600 for a 40-acre field. These annualized costs are based on the full lifetime of the investment. So we're amortizing the thing and putting it to, this is what it would be like for you on a per year basis. Would you invest in drainage tile at 60-foot spacing if there was a 10% chance that you get $21,200 versus a 90% chance of $22,400? And the difference there is, okay, and sorry, and this first one is if they invested in the drainage tile. So this mitigates the downside risk. If they do not invest in drainage, they have a 10% chance of getting $20,000 and a 90% chance of getting the full return on the field without the cost of investing in the drainage tile.
Is that because they don't lose anything in terms of area? Or do they get more?
So here, the 24,000. So if you look at the difference between the 24,000 and the 22,400, both of those are cases where there was not too much rain and drainage was not important. So in this case, they did not invest and they don't incur any cost. In that case, they did invest in the drainage tile, but they didn't actually need it. Yeah, that's the 1,600. Okay, so one other thing I should note, with these agricultural lotteries, we didn't have as fully varied an experimental design as we did in outcomes. These were all positive outcomes, and there's some consequences for that. We weren't able to estimate as successfly risk aversion functions from the agricultural lotteries. So we did moderately well, but not as well. So how?
Presumably you're varying your probability.
No. The probabilities vary and the payoffs vary. But in the agricultural lotteries, they were always positive payoffs. We didn't structure, wisdom of hindsight. We probably should have done this differently. We consulted with agronomists about, what they would expect as different returns. And I think we probably should have forced a little bit higher variability into it than we did. So we used binary probelet to estimate these risk utility functions based on random utility model. The key point I want to make here, because we had 25 general lotteries per person and 18 agricultural lotteries per person, we're able not only to estimate measures of aggregate risk aversion across the 44 farmers, but we can also estimate coefficients of risk aversion for individual farmers, and we're going to use that. So the aggregate models, there are three takeaway messages here. First off, we see risk aversion across all models. So constant absolute risk aversion, this is a level of is slight absolute risk aversion, but really quite close to what a lot of the field measures have found. Constant relative risk aversion, when you see positive coefficients, this means these people are risk averse. In the expo power function, there's a little offsetting effect there. There's a strong relative risk aversion coefficient, but kind of surprisingly, a negative absolute risk aversion coefficient. When you combine them together, you get risk averse behavior. The second takeaway message is that if you compare the general with the agricultural values, we see that by a significant degree, the farmers are more risk averse for agricultural investments than they were for the general ones. Yes, so this is highly significant difference. Here, they're close, yeah. And then finally, the best fit model, statistically, was the expo power function. But for the agricultural, lotteries, there's no meaningful difference in the likelihood functions between the expo power and the constant relative risk aversion. Okay, those are the aggregate results. And we also were able to do this individually. And let me talk you through what this picture says. Remember that I said that with the expo power function, if that R coefficient is 0, then the expo power function reduces to being constant absolute risk aversion. If the alpha coefficient reduces to 0, then we have constant relative risk aversion. So what this is showing us is that in the general lotteries, when we run Wald tests to see, can we test the hypothesis that R equals 0, we reject the hypothesis that R equals 0 in almost all of the cases. And so, and that's also true in the majority of cases for the agricultural lotteries. So when we look at individual risk preferences, we're seeing that they are not consistent with absolute risk aversion. By contrast, on the general lotteries, all of them, we were unable to reject the hypothesis that alpha equals 0. So they're all consistent with relative risk aversion here. And in the agricultural case, they're dominantly consistent with relative risk aversion. I had mentioned to you that we weren't able to fit the expo power function because of design factors to all of the agricultural cases. I told you we had n equals 44, and the reason that you see columns that go up to 32 is because those are the only ones where we could run these tests. All right. So without dwelling on this slide, what we basically came out with was that the best functions here were either the expo power function or the constant relative risk aversion function. They basically came out. We have a variety of criteria here, and I think there's not really time to go into them. But it was sort of tie, and in a tie, I will pick the more parsimonious model, and that also allows us to go with some simpler theory that we'll come to next. So, so if you pick the constant relative risk aversion model, then here we want to look at, and this is a question that came up at the ARES meeting, what factors affect risk aversion? So what we did here is we regressed their risk aversion, the estimated R coefficient for individuals against a set of other variables. And where you see R there, that's really the constant. It's not, we regressed R on this, but in the general lottery, you regress R on itself, you get a constant that's the average value. So what came out here was, in the general lottery, some evidence that people become more risk averse until, well, so it was a quadratic payoff, more risk averse until age 70, 71, and then they taper off. On the agricultural side, what we found was, with the same set of variables, the significant effect was that farmers of larger scale showed less risk aversion, and that's consistent. Although we have constant relative risk aversion here, what we're seeing is some evidence of decreasing relative risk aversion with wealth as measured by acres operated. Okay, so how are we going to use these risk aversion coefficients? One way to simplify things and kind of think what to expect here is to convert constant relative risk aversion into a mean variance model. And so thanks to some work by Jerry Nelson and Cesar Escalante, they worked out the math for us. And what this allows us to do is come out with a numerical measure of that risk premium that I showed you on the graph that is equal to the price of the output times that risk aversion coefficient times the effect on variance that comes from applying an input A. And the input A that I'm interested in here is an input that could be a risk-reducing input. So if A is a risk-reducing input, then the derivative of variance with respect to A will be a negative number. And what we'll get here is that the decision maker would be willing to use more of this, would want to use more of this risk-reducing input than they would if it was simply based on maximizing average profit. So that's basically what I just said with the negative sign there. So our expectations are that farmers will want to adopt adaptation inputs first off if they boost yield. Like, they'd always want to do this even if they didn't care about risk. But they'd also like to adopt them if they reduce variance, and especially if they reduce not just variance but downside risk, which I've called semi-variance here, but it does. Semi-variance is assuming that we have a symmetric distribution. We don't have to assume that. Okay, so what we did was we elicited triangular distributions, and this is like the simplest possible way to elicit probability distributions from people. You say, what do you think is the worst possible outcome? What do you think is the best possible outcome? And in between those, what do you think is the most likely outcome? And there are formulas to calculate mean and variance from those. So how did we do this? Well, we said to farmers, suppose you acquired a new field that is similar to your current fields, but it does not have irrigation, does not have tile drainage, and it does not have drought-tolerant seeds on it. Please think back over the past 10 years and picture what corn yields would likely have been on this field if you're using your current hybrids, your current seeds, but under past weather conditions. And then, over the past 10 years, what do you think would be your lowest corn yield, your most likely yield, and your highest possible yield in bushels per acre? We asked them to do this with the original setup, with no investments in the field, to think again, now what if you just had irrigation in that field? Think again, what if you had just drainage tile in that field? And what if you had drought-tolerant seeds? And then we asked them to do this same exercise for the future 10 years. So this is what we learned from them. With no investments in the field, they are expecting that over the next 10 years, they would have a little bit higher yields. And it's a little bit hard for you with the naked eye to see, but they also expected a slight increase in variability, but the increase is more on the upside. So we're actually in a part of the Northern Hemisphere where farmers are likely to benefit some from at least from longer cropping seasons. Now with center pivot irrigation, farmers, compared to nothing, they expect much higher yields, both in the past and in the future. In the future, they're expecting a little bit more variability, but again, the increase in variability is on the upside. So it's actually a smaller downside, but if you measure variance, we're going to see a little more. With drainage tile, again, higher mean yields, a little bit more variability, smaller downside. And finally, the drought-tolerant seed, higher mean yields, no real change in variability. And when I talk about the downside, you know, this is the lower triangular part of the distributions that we're going to look at. So how does risk aversion, all that risk aversion coefficient stuff that I went through earlier, how does that affect what farmers are expecting in terms of probability distributions? Well, to get that, we regressed the standard deviations of the yield probability density functions on R, on those R coefficients that we had estimated earlier. And we found that risk aversion increases perceived standard deviations for certain distributions, drainage and drought resistant seed, and on the others it had no significant effect. So it never decreased them, but it didn't increase them in very many cases. Now, jumping to what farmers expect that risk reducing investments will do in the future. So if I plant, if I invest in irrigation, what we're looking at the changes in these probability distributions from past and future. What are they expecting the changes to be? And let's just look at irrigation, for example. So in the past, they viewed irrigation investments in the past 10 years as reducing variance. And but over the future, they don't see any change in variance. In the future, well, in terms of mean increase, you saw those triangles moved up. So they expect average returns under irrigation to increase for both. So what we're seeing here is that for irrigation and drainage, they see big increases in mean values. And in fact, there's been a lot of past investment in drainage. So relative to our expectations, the mean category here is what anyone who is indifferent to risk, just cares to maximize profit, they'd be interested in. We're seeing strong evidence for these. On the variance reduction side, there is some evidence of benefits, certainly for drainage, and the drought tolerant seed beneficial for risk reduction, but not meaningfully for yield gains. So what we're finding then in terms of farmers' adaptation choices is that risk aversion increases perceived variance of crop yield in some cases, and this is similar to what Menepace et al. Found in Italy. But it has risk aversion doesn't particularly influence how risk reducing inputs will affect yield. The preferred investments to reduce yield risk are drainage tile and irrigation. So drainage tile is already quite common in the region. It raises yield, it reduces the lower semivariance. Irrigation raises the mean and also reduces the lower semivariance. Drought tolerant seed, this reduces the variance, but not much difference in yield. So our key findings: first, farmers are more risk with agricultural investments than they seem to be with general risky gambles. Second, they perceive that future weather will raise mean yields, but also increase risk, although mostly that's upside risk, frankly. And they prefer inputs that reduce weather risk, but are win-win, that boost mean yield while also curtailing downside risk. Key messages for policymakers trying to think about how farmers, policy for climate change adaptation. First off is understand the farmers. If you want to understand how farmers will adapt to changing climate, you'll see lots of articles by academics about, climate change forecasts, and those have value, but the decisions get made by people based on their subjective probability distributions and what they believe will happen. And so it's important to understand those beliefs as well. Both those beliefs about the changing distributions and beliefs about the efficacy of particular risk-reducing inputs. Crop insurance is a key policy tool in this that we are looking at separately, but it's also one that's very widely adopted in the United States because it's tied to getting benefits from some of our other agricultural policies. So it's not going to shift outcomes very much for farmers. So finally, this is the lead author of the paper, Natalie Loduca, and we thank our farmer interviewees for the time and effort that they put into this. And this is a non-random sample. We recruited this sample through people in the University Extension Service and through people in the Michigan Corn Producers Association. So the kind of people who participated are scattered across the southern part of the state. We made an effort at representativity in terms of the kinds of location, but there's certainly going to be some sample selection bias in terms of the kind of person who already had a relationship with extension personnel and was happy to spend an hour with a professor or a graduate student. Okay, well, there you have it.
Okay.
Yeah. Oh, I saw Danielle.
Sorry, just a quick question. Did you find any similarities with the strategies that farmers are following to hedge their market risk?
No, Emmanuel, I don't know what their strategies are for hedging. I mean, we didn't ask these farmers about managing market risk. The only thing we asked these farmers was relative to markets was about their future price expectations, because in our statistical models about how they would behave for the future, obviously the value of the product is important. For the past, they simply experienced that, so we didn't elicit that. But we don't know about their market risk reduction strategies.
In general, they were expecting more volatility around prices or not?
We don't know. We only ask them about yields.
Oh, just sorry, yeah.
Yeah. Michael.
If I understand this right, you're asking the farmers when they're doing the yield questions to hold quite a lot of stuff constant. Is that right? Looking back at this field, saying what do you think the distribution would have been with, say, current irrigation technology? Now, going forward, this field's future, but with the current irrigation, I'm just wondering how easy it was for people not just to get the prior sort of default setting of stuff gets better, irrigation technology gets better, things that higher yields. Do you get any sense as to whether they could actually sort of partition their brain in that way to actually abstract from it, if that's what you're asking them to do?
So that is what we were asking them to do, and you know, you're familiar with stated preference elicitation practices, and we did considerable pre-testing here, but and that led to what would be called the cheap talk script, and I actually showed you parts of it, but the cheap talk script walked them through, you know, encouraging them to think about this as if. But with that said, can I truly avow that their expectations of future improvements are only because of climate and not because of some embedded sense that, you know, seed technology has always been marching forward? And it has been, especially, you know, I don't know how much maize is grown in Australia, but the progress in maize genetic yield improvement over the past 80 years has simply been phenomenal. It's about 1 to 1.5% year yield increase over a very sustained period. So are they confounding that? It's entirely possible. Yes?
Just interested in causality, you know, what does risk aversion, is risk aversion affected by the variance, or is, well, you're saying variance is affected by the risk aversion. Well, it's not clear to me which way the causality runs there. And also, did you consider measuring loss aversion?
So on the first question, because we were eliciting subjective probability distributions, I think you can make the argument that risk attitudes, which are built from a variety of personal experiences, that those would shape subjective probability distributions. Had we been looking at objective probability distributions, I don't think you could make that claim at all. In terms of loss aversion, we did not measure that specifically. That might have been a good idea. One of the things that all of us struggle with when we when we design surveys, whether they're online or in person or whatever, is what not to include, because you know that you're working within a kind of implicit time budget constraint. And if you want people to pay attention, you can't go on too long. And so we didn't do loss aversion.
But then the general risk aversion hesitation, it might have actually been very positive, because if you go into the negative as well, then the risk aversion and loss aversion can interact, and you get misinterpretation of the results. That just adds. Following up on this, you highlighted the importance of downside risk. How do you think that would that have been picked up with prudence? Go yin, the third derivative of the utility function, which I'm just thinking I had an opportunity to learn about cotton growers in the eastern part of Australia, mostly in Queensland, and a PhD student who didn't finish showed that you couldn't actually understand what was going on using measures of risk aversion, but you could elicit what was going on using prudence in the technical sense, which is focusing on downside risk. Mm-hmm. That's my question. Also, I'm not sure how that might relate to what you call lower semi-variance. I think it's two different things, but I'm not sure.
Well, Steve, this is something that maybe we need to follow up on, because I know that there's a literature out there that gets into the third moment of distributions, and that would allow us to look at skewed distributions that are skewed to the downside. Yeah. So, but we didn't dig into that, and yet it's one of these, one of the cool things about research, and I'm kind of saying this partly for the graduate students in the room, is that you start out with a certain plan. And if you're doing interesting applied work, you almost always find that things don't quite turn out as you expected. And you can just say, oh, well, turned out different. Or since we're in the business of learning, you say, well, gosh, why was that? Let's see, what could we do more? And so this is a case where we're now thinking, all right, we're seeing empirical evidence of reductions in downside risk, even though variance may not have changed. And so anyway, Steve, that's an area that I'd like to explore a little bit more.
Yeah, because if I remember a few years back, the impact of increased variance was smaller than the perceived increase in downside risk, which is what prudence actually picks up. And it has a completely different kind of behavioral implication in terms of investment.
Mm-hmm. Okay. Well, I'm going to follow up with you on that question.
Can we just do some online ones? There's
yes.
Quite a lot online.
Oh, goodness.
So we've got one from Lindsay Bell. Lindsay, would you like to unmute yourself, or would you prefer I just read it off the chat?
I can unmute myself, James, if it works.
Let's go. I can't even see you.
That's right. How are you all in WA? So my question is, did you pick up any difference in the cohort in their attitude to the larger investments that you were posing to them versus the smaller ones, which might have been more appetite for risk involved because they're smaller and more regular?
So Lindsay, we didn't we didn't parse out the difference within an investment. So all I can say is that we had one category of investment, which was the drought-tolerant seed, where it was much less costly than the investments that involved actual land change in drainage tile or in irrigation. And so, but it also had less effect on means. So I don't know, I guess I can't really answer your question well, because answering your question well would require splitting the data between those that had less expensive investments and those that had more within some of the same categories.
Okay, let's go with Ross. Ross, do you want to unmute?
Sure, I'm not sure if you can hear me or not, Scott.
Yes, I can.
Great to talk. So we know in Australia that farm size is always trending upwards, and I don't know if that's the same in your study region, but you're finding that larger farmers were less risk averse. Given that climate change is a long-lived trend, that's going to be accompanied by increases in farm size. So does this mean that the farmers in the future, because of their increases in farm size, may actually be less risk averse on average than farmers, say, 10 years ago?
I think it does, yes.
Very well, that's a simple answer. Okay, we're getting towards the end of time. Do you want to elaborate further? No? Okay. So we've got last question up here.
Yeah, I'm just a bit curious about the actual farmers. So I would like to know about the age distribution, if the young guys were more or less risk averse, and I'd also like to know about their experience, first generation, second generation, how long they've been on farm, and also gender.
Okay. Gender is the easiest one to answer. All 44 were men. And a kind of general pattern that we see among farmers in the Midwestern United States is that in grain and oilseed crops, the field management is dominantly done by men, but many are operations where there's a woman who does finances, does more of the office work, thinks a lot about the marketing. So there are many partnerships with close involvement of women, but dominantly when it comes to like who's out in the tractor and who's deciding on which variety to plant, it tends to be the men. On age, the median age of a farmer in the United States is now 59 or 60 years old. And that was pretty true in our sample. The youngest people were maybe in their 30s, and then they went on probably into certainly into the 70s, into early 80s. What was your first question?
Oh, well, if those young guys were more or less risk averse,
Oh,
and if maybe the older guys have been on farm longer, seen more seasons, had seasons more.
well, and that's something that was a little bit surprising to me. But it seemed as though people got, the younger guys were a little bit less risk averse, but as they aged, they got more risk averse until they got into their 70s, and then it began to taper off a little bit. And I think that's a little bit, no, but honestly, risk aversion, it's hard to separate the kind of inherent attitude from vulnerability to risk. And by the time that someone's in their 70s, they've probably, in most of these cases, they've built up a good deal of asset value. So now the consequences of bad outcomes are not so bad. And so they, I think that's probably a little bit behind the pattern that we're seeing.
All right, I know there's at least one more question online and there's more in the room, but we're at time. So feel free to contact Scott one way or another and ask any further questions. But can we thank Scott for the fantastic presentation?